I would like to thank the organizer. It seems I cannot share my video, by the way, but can you see my talk? Do you see? Do you see? Okay, all right. So I start by thanking the organizers, and I thank Professor Jamil for inviting me. And this talk is in algebra, and I tried to make it like accessible to graph usually are of interest, I believe, whether you are in pure math or applied math. So I decided to talk about graph. This is a recent paper, just appeared in Communication in Algebra with my co-author David Anderson. Before I start giving the details of this paper, I would like to share with you this beautiful result. Here is a question. You might think this question, somebody already answered it. I mean, this is very classical question. When is the polynomial ring over a commutative ring is a principal ideal ring? Of course, we know some cases when R is a field, but can we have a complete characterization of all rings where the polynomial ring over R is a principal ideal ring? And remember what we mean with the principal ideal ring. That means every ideal is generated by only one element. Okay? I get to know the result about, a complete characterization maybe in March. So we're talking about maybe 3 months ago or something like that. And this is the title of the paper. And these are the names of the authors, Henry and Lopez. And look at the answer. Answer is very surprising. And you might think, look at the answer. The polynomial ring over R is a principal ideal ring if and only if R is ring isomorphic to a finite direct product of fields. Wow, this is just amazing. The characterization is just amazing to me. And this result just appeared in 2018. And you would think somebody already did that like long time ago by Kaplansky or, others, Gilmer or whoever. So whenever I come across this result, I get excited. And for me, this is one of the most beautiful result I came across maybe in the last 10 years because it make many things so trivial. So all of us know if R is a field, then this is true. For God's sake, just let n equal 1. Then you get it. All of us know that if you have a field, f, and you add two variables like x and y, then this is not a principal ideal ring. Why? Well, what is f x comma y if you add two variables? This is f of x, your ring R, and you add to it y. But f of x is never a field. Never. And from out of this, you end up that the integers modulo n, the polynomial ring over the integers modulo n, will be a principal ideal ring if and only if n is square free. And all these things, and maybe you come up with something more than that, and all these result just by staring at this beautiful result. So I thought I share this with you before I start my talk. Okay, so let's go back to graph. Okay, I see some chat. I'm not sure if this is for me or... okay, so I keep going. So you're still hearing me, right? Okay, okay, that's fine. Okay, so we let R, let me take you back some history. If R is a commutative ring and ZR is the set of all zero divisor of R, then in 1999 we have this zero divisor graph. And maybe if you are in algebra, at least you heard about such a graph. And what does this graph consist of? Because whenever you have a graph, you have vertices and you have edges. The vertices are the non-zero zero divisor of the ring. And how do you connect two vertices, x and y, are connected if and only if when you multiply them, you get zero. In 2002, we have three authors here, DeMeyer, McKenzie, and Schneider. They generalize the zero divisor of commutative ring to zero divisor graph of commutative semigroup. So they remove ring and they study semigroup. Okay? And how they define it, they let S to be commutative semigroup. You can think of the operation as multiplication with the zero element. Okay? And what are the zeros of the commutative semigroup S? As usual, all the element x in S, where xy equals 0. And this set, if you remove the 0, you see ZS star, which is the set of all zero divisor of the semigroup S, removing 0. Okay? These will be the vertices of the graph, and you connect in the same way. And in fact, if you think about it for a minute, for any ring, the zero divisor element of any ring is always semigroup, right? Is always a semigroup with 0. So this is a very natural way to generalize to semigroup. You don't need the whole ring, but definitely you're gonna see, and if you are, you know this area, that when you are inside commutative ring, you still get what I call maybe more interesting result about the structure of the ring. Okay, and all right, so that's enough about the history. Here is the setting for my talk. S is a commutative semigroup, and you fix a positive integer n. And what is the set ZNS? Z index by NS. You take x to the n, where x is a zero divisor of S. Okay? So you take the zero divisor of the semigroup and you make each element to the power n. All right? Okay. So definitely this set, it will be also commutative sub-semigroup of the zero divisors of S. That's very easy to check. because remember that the zeros of S is a subgroup of S, right? And what is ZNS? I'm going to the zero divisor of the semigroup S, and I'm taking powers of this element. And remember that my n is fixed. Like if you let n equal 2, then Z2 is different from Z3, right? Okay, so we define the N-zerodivisor graph of S. What is it? Well, the notation is gamma indexed by n. Again, this is the N-zerodivisor graph. What are the vertices? Are Z, the ZNS star, meaning, as I mentioned earlier, if you stare at ZNS, what's ZNS? You go to the zero divisor of the semigroup S, and you raise each element to the power n, meaning x times x times x n times. But you remove the zero. And how do you connect? If you have two elements in the Zn as star, you connect in the normal way, xy equals 0. Okay, let me stop for a minute here. What about if n is equal 1? If n is equal 1, this is nothing but the the classical zero divisor graph of S. So clearly, the work we did here generalized the whole concept. N does not need to be 1. It could be 2, could be 3, could be 4, and so on. Okay, so to continue with my talk, you only need two things. You need to know what is my graph. My graph called gamma indexed by n. What are the vertices? The vertices are you take element in the zero divisor of the semigroup, and you make all the element to the power 0. To the power n. And you remove the 0. Because if I keep 0 there, then the graph is not really you don't get anything. It will be everything connected. Okay? All right. So here is the first result. This is a complete answer for when is the gamma n s is connected. What do I mean with connected? It's just in the normal way, like you can go from one vertex to another vertex by a path. Okay? All right. So when you tell me that the N-zerodivisor graph is connected, this is equivalent that for every x in Zn as star, there should be a y in Zn where xy equals 0. Okay? In another way to say that the zero divisors of the ZNS star has to be ZNS star. Okay? Because remember that here is something crucial. Because maybe you have a vertex like X and Y are connected in the semigroup S. X to the N is not 0. So X to the N will be definitely in ZNS. But maybe Y to the N is 0. And remember in the graph, N-zerodivisor graph, I'm removing the 0. So maybe you think that now you have X to the N, maybe there is nothing connected to the x to the n. Why? Because the element y that is connected to x in the original graph, when I raise y to the n, becomes 0. But 0 is not a vertex in my new graph. So you see the crucial thing here in this work. But to be connected, I should always find a y. So if x in ZNS, I should always be able to find a y in ZNS star where the product is 0. Okay? Otherwise, the graph will not be connected. Okay, imagine it is connected. Then the diameter can be 1 or 2 or 3. What do I mean with the diameter? The diameter, like let's see the diameter of the graph is 2. What does that mean? I can go like choose any two random vertices. Let's see V1 and V2. Then I should be able to find a path that consists of exactly two edges. Like maybe I can go from V1 to V3 and from V3 to V2. Okay? So the diameter is the maximum of all distances between the vertices. But in the street language, when I say the graph has diameter 2, that means I can go from one vertex to another by walking, like I walk over a maximum 2 edges, and I should be able to reach V2. That's the meaning of the diameter to be 2 or 3. Okay, what is the girth? The girth is the shortest cycle. And a cycle could be, you know what a cycle, you start from one vertex and you go around and you come back to the same vertex. And the shortest cycle, that's what we mean with the girth. It could be 3, meaning a triangle. I could have a triangle, or I could have a square, or infinity. What do I mean girth infinity? Girth infinity, it tells me that my graph is a tree. There is no cycles. My connected graph, when my connected graph has no cycles, it is a tree. And we say the girth is infinity. Okay? Okay. Here, we assume S to be a reduced commutative semigroup. Then I don't have, look, in the first theorem I gave you condition when is the N-zerodivisor graph is connected. But if my semigroup is reduced, what do I mean with reduced? That means x to the n equals 0 if and only if x is 0. Okay, that's when if you have a semigroup that satisfy this condition, we say that the semigroup is reduced, meaning x to the n equals 0 if and only if x has to be 0. In case of the ring of the semigroup is reduced, then the graph, the N-zerodivisor graph, is always connected. And look at this. dn, what do I mean with dn? dn is the distance between xn and yn inside the N-zerodivisor graph. Okay? Because x and y, you know how x and y will be non-zero, n-zerodivisors of the semigroup S. X to the n and y to the n are definitely in the zero in are vertices in the n-zerodivisor graph. If I measure the distance between x to the n and y to the n, what I mean measure the distance? The length of the shortest path. What do I mean with the length? The length here mean how many edges does my path have? Like if I go from V1, V3, V2, that means I'm using 2 edges. If I do V1, V3, V4, V2, that means I'm going from V1 to V2 by using 3 edges. So the length will be 3. What this result tell me that the distance between x to the n and y to the n inside the n-zerodivisor graph, it will be the same distance as x to the n and y to the n inside the classical zero divisor graph, which is the same as the distance between x and y. It's kind of interesting. Okay? And of course, here we assume x to the n not equal y to the n, because we don't allow loop. Okay. Let's look at this result. What does it say? If you have a reduced commutative semigroup and n is a positive integer, and you choose x and y to be non-zero zero divisor of the semigroup S, and assume the distance between x and y is 3. Wow, look at the conclusion. If you only find 2 vertices where the distance is 3, only 2 you need to check. Then the diameter of the n-zerodivisor graph has to be the same as the diameter of the classical zero-divisor graph and has to be 3 for every positive integer n. So as soon as I find 2 vertices, okay, where x to the n and y to the n inside the n-zerodivisor graph, the distance between them is 3, then I know quickly what is the diameter. Okay? All right. Okay, here we have also, we assuming S is reduced again. And let's look at A and B and C. So my semigroup is reduced. And let me remind you what I mean with reduced. Sorry, reduced mean the smallest, meaning whenever I have x to the n equals 0, that means x has to be 0. Okay. If the diameter of the M, of course here instead of N, I'm using M. The diameter of the M zero divisor graph 3 for some M, then I don't have to, like imagine you selected M to be 2. And you look at the 2 zero divisor graph of the semigroup S, and you discover that the diameter is 3. Then you don't have to, then I know something about the diameter of the classical zero divisor graph, and I don't have to check for any more integers. If you change 2 to 3 or 4 or 5 or a million, still the diameter of the n zero divisor graph is still 3. will be the same, will not change. Okay? If the diameter of the M-zerodivisor graph is 1, then the diameter of the classical zerodivisor graph could be 1 or 2. And then, what about if I change my M to another number, N? Then the diameter of the N-zerodivisor graph will alternate between 1 and 2. Okay, so if the M-zerodivisor graph, the diameter is 3 for some M, then stay 3 for every N. If the diameter of the M-zerodivisor graph is 1 for some M, then what can we say for every other? It will alternate between 1 and 2. What about if the diameter of the M-zerodivisor graph is 2 for some M? It's still the same. The only difference between B and C, if the diameter of the M-zerodivisor is 1, then the diameter of the classical zerodivisor could be 1 or 2. Where if the diameter of the M is 2, then the diameter of the classical zerodivisor will be 2. And the other condition is still the same as B. If you change M, then, and of course, you're going to ask me, we have examples of every case, but I did not mention them in this talk. So in every case, we have an example. The paper is already long, like 24 pages, I believe, because we have many examples in this paper. Okay. Okay, I'm still working with the reduced case. If your semigroup is reduced, then the following statements are equivalent. If you tell me the girth, remember what is the girth? Is the length of the shortest cycle. And how we measure the length in graph theory? Length in graph theory, you count how many edges you use in the path. Like here, the girth equal 3, you think of a triangle. Okay? So like you have A, B, C, A. If you know the girth of the classical zerodivisor graph 3, then I know the girth for the N-zerodivisor has to be 3 for some N. Okay, for every N. Look at number 3. So if you tell me the girth is 3 for some N, the girth of the N-zerodivisor graph is 3 for some N, then I know that the girth of the classical has to be 3, and the girth of the N-zerodivisor graph has to be 3 for every N. Okay. All right, here we still my semigroup still reduced, and now we change to the girth to be 4. If you have the girth to be 4, then the girth, so the original graph, girth of gamma S. What do I mean the girth of gamma S? The girth of the classical zerodivisor graph is 4. Then the girth of the N-zerodivisor graph will be either 4 or it become a 3. So you alternate. And we have cases, And we have examples where sometime will be 4 and sometime will be a 3. A 3 meaning girth is infinity. Okay? If the girth, or if your original graph is a 3, then the N-zerodivisor graph will stay as a 3 for every n. Remember that when I mentioned that the girth of a graph is infinity, that means no cycle. And since the graph is connected, then we call it a tree. And remember, if from the first result, if your semigroup reduced, then the N-zerodivisor graph is always connected. Okay? However, if the girth of the M-zerodivisor graph is 4 for some M, then I know that the girth of the original graph, the classical zero-divisor graph, is 4. And again, if you have a tree, if your graph is at, if the M zero-divisor graph is a tree for some M, and then you start changing M, you're playing with M, then sometime you're going to have girth 4, and sometime you will have a 3. It will like go back and forth, alternate. Well, maybe not alternate, but as I told you, we have examples of every case. Okay, and here is a result. We conclude that if the girth, if my ring is commutative, now let's go back to the commutative ring, because any ring is a commutative ring. Definitely is what is a semigroup. So if R is a reduced commutative ring, then the girth of the classical zero-divisor of R will be the same as the N-zerodivisor graph. It will be the same as the girth of the N-zerodivisor graph. And if the girth of the classical zero-divisor graph is 4, and the girth of the N-zerodivisor graph is infinity for some N, then what you gonna say about the next one? Look how this works. The girth of the N plus 1 will be 4. Or the girth of N times N plus 1 is 4. All right? So what that means, if the girth, that means the shortest cycle in the classical zero-divisor graph is a square, and you assume the N-zerodivisor graph is a tree, then it will not stay a tree for all N. Then one of these has to be true. Either the N plus 1 zero-divisor graph will have girth 4, or the N times N plus 1 zero-divisor graph will have girth 4. And of course, there is a proof of that. Okay. Here is what I call it structure. Like, remember that why we study graph. I mean, like for us in ring theory. Well, I mean, one of the main reason, can we get some information about the structure of the ring, like some properties? One of them is this theorem here. If your ring is reduced, then the following are equivalent. There is Hello? Did I get disconnected? Hello? Well, this is, as I told you, this is like a theorem that gives me some information about the structure of the ring. Like if I know that the N-zerodivisor graph of a reduced commutative ring is complete bipartite. That's what KMN. KMN, that means my graph is complete bipartite. Then, of course, number 2 is trivial. Interesting that the girth of the original zero divisor graph will be 4, but look at the structure. What is TR? TR is the total quotient ring of R. The total quotient ring of R has to be a product of two fields. Okay? That's interesting. And here is another result also. Let's read the last one. If the girth of the N-zerodivisor graph is 4, then also I know the structure. I mean, all these results deal with the structure of a reduced commutative ring. Okay? You can look at that. What's K infinity infinity? That will mean complete bipartite, and my ring has to be infinite, right? That means I have infinitely many vertices. If your ring is, I think I have more. I believe, let me see. I think I better stop. I just shared this last result with you. Here is the question. If you are interested, of course, you can always send me an email and I will be happy to send you the full paper with details on this subject. Okay, to be brief, to end up my talk, I'm going to tell you something. If your commutative semigroup is reduced, then the N-zerodivisor graph is always connected. You're going to tell me, is that true in general? What about if my semigroup is not reduced? What do I mean not reduced? Meaning I have an x that is not 0, but x to the n equals 0. That means my semigroup is not reduced. Then the graph could be connected and could be disconnected. It's not always connected. And that's where kind of interesting here, because we know the classical zero divisor graph for any semigroup is always connected. That's true for the N-zero divisor graph if your semigroup is reduced. But if it is not reduced, then the classical zero divisor graph is always connected. But the N-zero divisor graph, we don't know. Maybe connected, maybe not. Here is a case where it's always connected. In this theorem, if your ring is a pi regular ring. What is pi regular ring? You can read the definition. You can think of the integers modulo n. And as an example, take the integers modulo n, whereas n can be any, integer bigger or equal to 3. Then the N-zero divisor is always connected.
Okay? So if your ring is pi regular, then the N-zerodivisor is always connected. And that's where in one of the cases where the N-zerodivisor graph of a non-reduced commutative semigroup will be connected. One of them, if your ring is pi regular. And here are some references. I just play them.
Okay, and I thank you, Jamil, for inviting me. And I'm sorry I teach summer school, and I finish around. I have a break now, and then I go back at 2, and then I finish at 4. That means 5 p.m. Uh, that means 3 p.m. your time. Yeah.